So just a reminder to everyone that the assignment that was going to be due opening tomorrow at midnight is no longer opening tomorrow at midnight. We're postponing it a week. Or if it was going to be next week, then we're postponing it another week. I don't know anymore. I think it was the 5th, 6th, so we're postponing it to the 12th, 13th. So you're not going to have that to worry about, or not immediately. So what I want to do today is I want to wrap up some carbonyl chemistry, and I want to introduce some ideas with carbocations. I know that, frankly, I think the experiment failed. Tried to take the advice of the textbook and provide carbonyl stuff first. I don't think that's worked out very well. So I think I'm going back to the other things. So we might circle back to some of these problems. So if people still have issues with this, we will be coming back to some of these things that people are talking about here. And our hands going up. So Mackenzie. Anything in particular, Mackenzie? Just playing with the hand button. Hands up. Down. Okay. Okay, I'm gonna assume it's supposed to be down. That's okay. So last class we left off with this, where we were saying, okay, there's a way to make an ester. We can use this thionyl chloride on an acid, make an acid chloride that we can then react with an alcohol to make an ester. And I left us with this thought, which is, well, why would you do that? We just showed on a previous slide that you just heat this thing with the alcohol. I hate my haircut. I actually just hate all barbers. I hate people touching my hair. Freaks me out. So my general strategy is I grow my hair so long until my wife tells me that I have to go cut it or I'm not allowed in the house. And then I go get it cut. And if I plan this properly, it's like every 4 or 5 months. And then I'm better. And my life is better. I actually never really worried very much about my hair one way or the other. It is bothering me that it's falling out. That's making me feel really old, because I don't think of myself as old. But then, you know, the hair falls out and it's turning gray, and there's a bald spot in the back, which you can't see from here. And I'm not turning around. And so it's, yeah, apparently that's an issue. Okay, this isn't a psychology class. Anyways, so I basically was saying, look, if we try and heat an acid and an amine, if you heat an acid and an alcohol, you get an ester. If you heat an acid and amine, you do not get an amide. And of course, an amide, the amide we would have made from this would have been that. But we don't get that. Anyone know why this doesn't work? Okay, my haircut might be the most popular thing I have done in this course. I try and not wear really offensive t-shirts on days I'm teaching. Any suggestions on why this doesn't work? So remember in the analysis, where we're talking about where reactions occur, you look for the most reactive thing, the H+, then we're going to protonate something. And so we're probably interested in what is the most basic thing. And we decided from last class that on the acid molecule, it was the carbonyl oxygen, which was the most basic. In this mixture of things, is that still the case? So I'm going to just start a new slide. You know, because you have to consider everything. So maybe we can rewrite this a little bit. And let's just say there's some inert solvent. So THF, again, it's an ether. It does nothing. just it's there. I could have just written, you know, random solvent number 2 that does nothing, but that's what I mean by THF. Random solvent number 1 that does nothing is dichloromethane. You just don't get hot enough. And I was saying that this does not make amide. So any ideas why not? There. Sweet, Alyssa, bang on. Okay, you're absolutely right. Where's that hydrogen going to be? It's going to be on a nitrogen. So we just made this. Okay, now if remember what we need to do, right, is we needed to protonate the acid to make this carbon more susceptible to electrophilic attack, to attack that carbon. And for that, we need a nucleophile. Alcohol is a good nucleophile. Is this a good nucleophile? I'll get to your question in a second, Jesse. Basically, is that, so what does something need to be a nucleophile? What is a nucleophile? We covered this. I promise. It is not a good, it doesn't have any lone pairs. Bam, it can't be a nucleophile. Like, it can't. You need lone pairs because you need the lone pairs to attack the thingy. You need the electrons, and it doesn't have any electrons because all of its electrons are tied up in bonds, so it's stuck. Not a nucleophile. So you make this stuff, and this stuff just stares at each other. Like nothing happens. But it's even worse than that because you think, okay, I'm going to be really, really smart. Really, really smart. I'm just going to add a tiny bit of acid catalyst. Aha, so only a little bit is like this, and a lot of it is free. Like that. Most of it's still NH2. I'm still screwed. Because, again, let's think. I need to activate this as an electrophile. I need to protonate that. I'm not doing that. Okay, I don't have a catalyst. You know, catalysts just make reactions go faster. They don't stop them from happening. Is there any other way that this acid can react with this amine? Besides drawing to attack the carbonyl, which we've been drawing, is there any other kind of reaction these two can do? Well, we've seen it. It's actually the first stuff we started with. If I had given you this question maybe 2 weeks ago, you all guys would have gotten it. But now, like, I've blinded you with carbonyls. Adding an acid. Let's be a bit more specific, Alyssa. Which acid? What do you mean by adding? You're on the right track, I think. I think you have the right answer. Just want to make sure. Nope. These two will just react together directly. We got smart by not adding an acid, not making too much of that. Deprotonate the hydroxyl. Absolutely, Brayden. Right? It's an acid-base reaction. The fastest reactions are acid-base reactions. This is one of those questions I would never ask you because it actually does require you to kind of know the pKa's. And it favors the right-hand side. Amines are protonated at physiological pH, like 7.4, pH 7. Amines are mostly protonated in water. Acids are mostly deprotonated. And so even though there are two charges here, which is not good, they actually prefer to do that because of pKa's. And I do not really understand that, so I don't ask questions like this. So that's unfair. But it's really dependent on the pH of the solution. And 1H is actually a pretty good nucleophile, because let's come back to Alyssa's question, which Alyssa was saying, why is the nitrogen the most basic site? Why is it more basic than oxygen? And let's just think about that for a second. Remember charge stability. The most important thing is the nature of the atom and its position on a row. And nitrogen is to the left of oxygen. So having a positively charged nitrogen is better than having a positively charged oxygen. Just like having a negatively charged oxygen is better than having a negatively charged nitrogen. It's kind of the exact inverse. And to get to Noor's comment, what I want to take a look at here, because that's a really good question, Noor, is let's just compare the last thing I want to discuss before we move on from carbonyls into something a little different. And I think I've frozen my computer screen. I have no idea what I did. It is not responding. Okay, just gonna plug it in. There we go. Is compare these two reactions. So I said you can't, with the esters, it was kind of a choice. To make the acid chloride. So if we walk through the mechanism there, we have the nucleophile attacking the electrophile, and we make the tetrahedral intermediate. So there's this intermediate here that's formed. We don't want to make 3 bonds to heteroatoms when we can make a double bond, because that's just not how carbon rolls. You could take that proton off. You could deal with the H at this step too. That would be okay. I'm doing with it a little bit later because it's just saving me a step of writing, because I want to make a point. Now, do exactly the same mechanism with kind of the nitrogen equivalent. Now there's no H plus that we need to react with. We just have this direct reaction. And we go to the product. So we have 2 identical pathways, right? They're completely analogous. Yeah, I'm recording, right? Good. let's take a look. So first of all, I think we're gonna roll into more talk about this a little bit later, but let's just discuss it right now. A thing called the rate determining step. It's going to come up in your labs. And this is the biggest jump in energy in a reaction coordinate. So we talked about reaction coordinates. So if we call this A, B, C, and D, and we have a reaction coordinate, energy going up, always label your axes. This is our reaction coordinate. Then, our starting material is reasonably stable. Our product is more stable. Okay, I'll come to that question too, Alyssa. I think I'm answering yours, and then I'll answer yours on with that too. We go up to a transition state. So this is A. I just labeled them with something specific, and I go and ignore my own labeling. A, D, B, C, D. So it's kind of like the bumps, and each of these is a transition state where the bond, we're going to get more into this a little bit later. For now, it's when the bonds are partially formed, partially broken. And again, intermediates are always valid Lewis structures. Everything I've drawn here is a valid Lewis structure. Transition states are not valid Lewis structures. They're in between. Bonds are partially formed, partially broken. So the question for the rate determining step is the most important step of a reaction. It determines how fast the reaction goes. Because once you can, if you can lower that, then everything else goes really fast. It's what slows the reaction down. And it's the biggest jump in energy in a reaction coordinate. So what is the biggest jump in energy? Is it going from A to B, B to C, or C to D? And it's always a harmful jump. So going up, you don't want to go up. You always want to go to the lowest possible energy. Yeah, A to B. I'm going to just abbreviate that as the RDS, so the rate determining step. Okay. So what normally is going to drive this reaction, what we can do to make this reaction faster is by making B more stable. So if we look at B and we compare the oxygen and the nitrogen versions of that, which one of those is more stable? Everything's identical, right? Except we got a positive charge on oxygen or we have a positive charge on nitrogen. Do you prefer a positive charge on nitrogen or a positive charge on oxygen? Please don't tell me you purged this already. Great, awesome. Exactly, nitrogen's more stable. So, which of these is more nucleophilic? Nitrogen or oxygen, the alcohol or the amine? And saying something's more nucleophilic means it does nucleophilic attacks easier. Or it does them faster, which is the same thing as easier. But you just told me the nitrogen was more stable. Yeah, it's the amine. Because the amine is more stable. This is more stable. So the BN versus BO, BN, like if this is the BO, BN is going to be lower in energy. It's going to have a smaller peak because the nitrogen is more stable. It's lower in energy. We always want to minimize energy, so it's easier to get to it. Yeah, the oxygen does have more electrons to give, but once it's given them, it's less happy. Nitrogen is not super unhappy being positively charged. Oxygen is. Like, again, going back to that whole where in the row you are, what makes this charge stable? It's where in the row you are, then you look at octets, then you look at, you know, down columns, and you look at resonance and induction and all that. I'm not caring about the end product here. I'm caring about this intermediate. It's all about what makes this rate determining step faster. And nitrogen makes the rate determining step faster. Because I've lowered the energy of that because I'm easier to get to that intermediate. Because it's more stable. So that means nitrogen is more nucleophilic because the step is faster. So things are more nucleophilic or less nucleophilic, or more reactive or less reactive, because they go fast. You know, that's what we mean. Like, we say that explosions tend to be quite reactive, and it's because explosions are very fast chemistry. They happen very quickly because otherwise you wouldn't have an explosion. And so reactive things react quickly. So the nitrogen is more reactive. Okay, next question was, why did we lose the chlorine here? Why did we bring the oxygen bond in and break the chlorine bond? Without making you memorize bond dissociation energy tables, which seems like the worst thing I can ever make you memorize, maybe I'll post. I'm going to see what happens if I type in bond dissociation energy into a Google search. Oh, I get a Wikipedia article with tables. Okay. So bond dissociation energy on Wikipedia, there's an article with tables. You can look at that, and you can look at the bond dissociation energy of a whole bunch of different types of bonds. It doesn't have everything, of course, because there's a lot of bonds. Definitely doesn't have the one we're interested in here. But a carbon-chlorine bond is a lot weaker than oxygen-carbon double bond. So we're trading, and even we're talking about this when carbon's making, if carbon is making 2 single bonds to oxygen, doesn't want to do that, it wants to make 1 double bond to oxygen. Carbon definitely doesn't want to make a single bond to chlorine and oxygen when it can make a double bond to oxygen, because chlorine carbon bonds are just not very strong. We're going to talk a lot about that. So this is a very favorable process. Why doesn't it kick out the nitrogen instead of the chlorine? Oh, it absolutely does. It takes us back to where we started. Because at this point, the nitrogen is still positively charged. It's still probably much easier to kick out. But if it does that, we go back to where we started, we come back, we go back, just, you know, we just shuffle back and forwards. Occasionally it kicks out the chlorine and we get to this situation, and then we can resolve it and we can actually move forward. So sometimes you just cycle back and forwards, but occasionally if there's something else that is feasible to happen, then you might do that to push the reaction forward so you can move on. I don't know if that answered your question about Alyssa, about the chlorine. I don't know if that helped at all. How do you know when you're right when you write the mechanism? Normally, I will give you either a product or, and so you need to be able to draw a mechanism to do that. Or I will, so I'll say provide the mechanism, or I'll never give you a mechanism product, I'll give you the reagents in the product. I think you're going to get a sense of these. So maybe right now, I have done a shitty job of this. So how about we come back to that and see if that's still your question, maybe in about 2 weeks. It probably will still be your question, how you know you're right, but maybe it'll be a slightly different version of that question. Like, what's a good way to check? Did everything make sense? Did you make any carbons with 5 bonds? Are the negative charges and the positive charges on the right things? Like, do they make sense? Are you creating unnecessary charges? Are you considering where the most reactive sites are on a molecule? And things like that. So let's take this to a couple of examples. So what I want to move on to is start talking about carbocations. So that's kind of carbonyl chemistry put to rest. We're going to come back to it at the end of the class when we tie it in with everything, and we're going to see analogies to it all the way through, and hopefully we can make some sense of some of this stuff. as we go, and it'll start clicking. So I'm going to actually just write carbocations. So we're moving from the red part, or this band of red in the schedule, to the yellow schedule now. Okay, what is a carbocation? It is a cation on carbon. That's a positive charge. So that's a carbocation. We have, what I want to talk, before we get into the details on this, I'm just going to try, yeah, we're moving on to lecture 14's material. So exactly, yes, we're moving on to lecture 14. So before I want to get into this, I want to just have a very, very brief, and it's highlight, well, you know, it's highlighted in the lectures. I talk about the stability of the different types of charges. And I just want to highlight a few things. I'm going to come back and I'm going to answer a few questions I got by email, which were on the previous material, I guess, so I'm kind of cheating. But I want to highlight a few things if you're looking at this, and I want to talk about hyperconjugation because I've gotten questions about hyperconjugation. What is hyperconjugation? And I think I talked about it in the lectures. I know I talked about it in the lectures, but I want to make sure I'm just really, really stupid explicit here. So a tertiary, this is called a tertiary carbocation. Why? 3 groups. 3 carbons attached. It's actually because there's 3 carbons attached. How many carbons? That is more stable than a secondary carbocation. Which is more stable than a primary carbocation. Which is infinitely more stable than a methyl carbocation. Now, you can even improve stability even further by having resonance. So any one of these can be, it can look primary or secondary or tertiary, but there's resonance it might not be, and we'll see some examples of that. But what I want to talk about is why, and I think I want to spend maybe the rest of the next half hour of this lecture, of this time, unless, well, next 15 minutes, and come back and do some of the questions we got. Talk about why this is the case, and the reason for this is hyperconjugation. Okay, so conjugation equals resonance. So more carbons is more stable, exactly. So conjugation equals resonance. So we would say that this cation is in conjugation with the double bond. Okay, so what the hell is this hyperconjugation thing? Well, it's not conjugation, it's not resonance, but it's kind of like resonance. I actually think hypoconjugation would be a better term, but because I don't think it's as good. And hyper means like better, but it's not really better. Anyways. So what is a cation? Let me go back to these questions here then. I've drawn a positive charge on these carbons. Carbon has 4 orbitals. We spent a lot of time talking about that. Where is the carbocation? So what I mean by that is, let's say I have this carbon molecule, and I say 1s, what is your your second electron shell? Is it sp2? Is it sp3? Is it sp? Is it s with 3 p's? It's got to be one of those things. And where are the electrons? 1s is easy. 2 electrons, always in 1s. Never do anything. 1s electrons don't do anything except for hydrogen. So Jesse is saying it's an sp3. So if it's sp3, that means we have 3 equal energy orbitals. Oh, we're getting a bunch of sp2s. So if it's sp3, we have 3 equal energy orbitals. Let's just think about what that means. You would have I'm just going to put the dotted ones, the ones it's sharing with hydrogen. So the ones from hydrogen are dotted, and then we would have an empty orbital. Because it's making 3 bonds, right? So it's going to have 3 of those electrons tied up in bonds. What do you think about that energetically? Does that make sense? That you'd have like 2 electrons in orbitals and then another orbital of exactly the same energy that's empty? You think we should fill the empty orbital? Yeah, you should, but there's no electrons. Yeah, it doesn't make sense, right? This isn't stable. So what if we say, oh, let's modify that so it's higher in energy? Now it makes sense, right? You got all the electrons filled in that orbital, and then you have an empty orbital higher in energy. But if you take from 1s, you always fill going up, right? You fill an orbital, then you'd still be positively charged. You'd not be screwing with your 1s. So you need a lot of energy to raise an electron from 1s to anything. 1s orbital electrons just do shit. They don't do anything. And I can say that with so much confidence. 1s orbital electrons do nothing. They might as well not be there. So that doesn't make sense. So so this, yeah, exactly, Alyssa. What I've drawn here, of course, this is sp2. So there's an empty p orbital. That is what a carbocation is. A carbocation is an empty p orbital. So let's say I draw out the diagram of this thing. I have a carbon. Now we started sketching these things before we were drawing wedges and dashes, but now we spent a few weeks building wedges and dashes. So hopefully now you're sort of seeing this in 3D. We have one lobe, one SP, and maybe this is like, oh, that's what he meant by that. We have one lobe coming out towards us, an SP2. We have one going back and away from us. We have one in the plane. And we have an empty orbital, and it's P. So if we think about this makes sense from a few perspectives. It makes sense when we start trying to draw this, because it's like, if there's an empty orbital, it can't be the same energy as filled orbitals. And actually, if it's a p orbital that's empty, then we're going from sp3 to sp2. And sp2 orbitals are lower in energy. They're more stable than sp3 orbitals. So the whole molecule can be lazier by being sp2. All of its electrons are, the average energy of its electrons is lower. If it was sp3, they'd all be higher energy, it would be bad. And then we have this empty p orbital, which would cost us energy if there was anything in it, but there's nothing in it, so who cares? It's kind of free. Like if there's nothing in the orbital, you don't pay the cost. So there's an empty p orbital. So it also means that the damn thing's flat. Carbocations are flat. Like pancakes. Or French toast. I guess waffles aren't flat. Well, I guess they are in the, anyways. So you have an empty p orbital. There's a positive charge in there. Is it accurate to say that that positive charge is localized entirely to that p orbital? Like, is there anything that we can do to help it? Is there any resonance? Is there any induction? No, there's bugger all. That positive charge is in that p orbital. That p orbital is like 0 electrons in it. It is just lonely and empty and is carrying this really heavy positive charge and has no one to help it. There's no resonance, there's no induction, there's nothing coming to help. Induction rarely helps with positive charges, but you get the point. Okay, now I'm going to change the molecule very slightly. I'm going to go to a primary carbocation. A shitty drawing. So I'm just going to highlight one orbital, and I'm doing this obviously to make a point. So think about a pi bond. So a pi bond is two p orbitals lined up next to each other perfectly, right? Each one has an electron. They can share electrons to make a new bond. Like they're lined up perfectly. Again, do we have any resonance? There is no other lobe. Everything's there's a hydrogen up there. There's like little mini lobes on the back of every one of these, but everything else is like a SP. Everything else is SP too. Like here's the p orbital with the two lobes, but everything else is SP3 or SP2. Yeah, there's no resonance. There's no real induction either. Everything's carbon hydrogen. It's really boring. Is there anything that's kind of lining up that if you squinted it kind of funny might look a bit like a p orbital, which I think I actually might have gotten Melissa already thinking about a p orbital, and it wasn't a p orbital, but she thought it might have been, and that's why she asked where the other lobe was, I hope. Or maybe not. Yeah, like if we look at this, it's kind of like half a p orbital, right? Like it's kind of pointing in the right direction. It's lined up. So these two electrons in here can kind of share some density. So you know what? They don't like, they're still making a CH bond, but the electrons can kind of stretch over and kind of sit a little bit in that positive P. Now they don't fix the problem. They don't make it not positive, but they make it a little bit less positive. And they move a little bit of the positive charge over onto this carbon and onto this hydrogen. Tiny bit. But a tiny bit matters. What we've just done, right, is by moving a little bit of positive charge over here, we've decreased this positive charge by the same amount. And if there's one thing charges like, it's being in many places at once. They don't want to be stuck in one place. On this methyl group, that charge was stuck. There is nothing it can do. It's stuck. On this guy, I can share a little bit with this sigma bond on the adjacent carbon. Now, if we jump all the way to a tertiary carbocation. Hopefully a lot of you are going, oh, I see what's coming next. I made a mistake by drawing this up too high, so I'm sorry. Close enough. A little bit off. Even I think that's shitty. In this case now, we have three of these that are aligned with this p orbital. So this guy can share a bit. This guy can share a bit. This guy can share a bit. Each one's taking a little bit of that positive charge away. This is what hyperconjugation is. It's the alignment of sigma bonds on adjacent carbons, or it can be on adjacent oxygens and nitrogens as well, with the empty or p orbital. So we're stabilizing that p orbital because we're able to donate electrons into it. And so we move the positive charge out of it, which makes it more stable. That's all it is. I don't think that's just, it's not a simple concept, but this is why we go back. We have this pattern. The methyl, there is no hyperconjugation. The positive charge is entirely stuck on that carbon. It's got nowhere to go. On the primary one, there's a little bit of help from this methyl group, one of those CH bonds. Which one? Doesn't matter. Constantly switching because the damn thing's spinning around like crazy. But at any one time, one of those hydrogens, CH bonds, is going to be somewhat aligned with that orbital, helping to stabilize it. This guy's got two of those effects, so it's more stable because two effects is better than one effect. This guy's got three of those effects because three effects is better than two effects, is better than one effect, is better than no effects. So what we see then is we see this increase in stability as we can increase the number of orbitals that can share electrons. That's hyperconjugation. And it's not like I've lied to you and tried to simplify it or do something like that. That is what it is. That is why that effect occurs. Is this why long carbon, depends what you mean by more stable, or. And because I don't know if we've talked a lot about that, they have higher boiling points. Is that what you're talking about? Yeah, the higher boiling point is not about chemical stability. Higher boiling point is about intermolecular forces, right? You have a bigger surface area, so you have more van der Waals interactions. That's not really due to hyperconjugation. That's due to electrons moving around in molecular orbitals. Van der Waals interactions are really complex. So the higher your surface area, the more of those you have, the more polarizable your molecules can be, the more you can generate partial negatives and partial positives all over the place and bind. This is entirely just on how many carbons are attached to the carbon. Samantha asked a critical question, and you're absolutely right, Samantha. The opposite happens with negative charges because you have the opposite problem. because suddenly let's just, so Samantha just asked, is hyperconjugation only applicable to positive charges or can it work both ways? Like a negative charge will be more stable on a primary carbon than a tertiary. Yes, a negative charge is more stable on a primary carbon than a tertiary. A negative charge is most stable on a methyl. It's not precisely because of hyperconjugation, but it's from a really related thing. So just for a quick second on that, because it is relevant, I guess. Let's take a look at the equivalent. What orbital is that negative charge in? Remember, the positive charge was in a p orbital. So what orbital is that negative charge in? Perfect, sp3, right? Because the positive charge was in the p orbital, which was good because it was higher energy and it was empty. We didn't have to pay the cost of putting electrons in there. But now there are electrons. That's what negative charge means, right? It's basically saying, hey, there's a lone pair on these carbons. And I don't want to put a lone pair into a p orbital if there's no resonance, because then I'm paying extra costs. I'm going to put into an sp3 orbital. So these are sp3. These are called carbanions. Anion on carbon. So they're sp3 hybridized. This is more so, in this case, it is the exact opposite of what we just saw. Now, the reason's not absolutely because of hyperconjugation, because now it's sp3, it's not sp2, so you don't have the same alignment kind of thing going. But let's think about this for a second. So I put 2 electrons into this sp3 orbital versus I'm not going to draw in all the orbitals on the other methyl groups. I'm just going to draw the one to the carbon. So hopefully you can forgive me this. Okay, so we'll compare these two. So thinking about the idea that electrons do not like being around other electrons, which ones of these would I prefer to be? So think about the fact that what I've just basically added is huge electron clouds, giant clouds of electrons. So these guys are sticking out from 3 giant clouds of electrons all around it. Like it's just surrounded by freaking clouds of electrons, and they're electrons and don't want to be near them. This guy, oh look, there's no huge clouds of electrons. It's nice and empty over here. I'm a happy negative charge because my electrons aren't being jammed around by a million other electrons. If you want, you can build a model kit of this. To approximate a lone pair, just don't stick anything on that carb, like just don't stick anything on the end of that, and just think the lone pair is sitting right there. And what you'll see is like the other methyl groups are all kind of crowding it, and everything's kind of close together. Versus if you just stick in hydrogens, everything's far away. So electrons hate other electrons. They're like Finns, like Finnish people. I'm Finnish. We hate other people. the old joke is, you know, if you settled on a river in Finland and you saw like any kind of cut wood float down a river, it was time to move to a new river because like somebody was way too close. If you can actually smell them or hear them, they're way too close, and your only choice is really to kill them at that point. So electrons are like that. They hate other electrons. They want to be far away from other electrons. So it's not, the logic is similar to hyperconjugation, but it's not hyperconjugation. It's about this. So Iacide asked, no, it wasn't Iacide, it was Noor asked, so why do carbon ions do this? Are they trying to preserve their stability? Like, what is the main purpose? Yes. Charges are trying to be as low energy as possible. Everything is trying to be lazy. You know, there's nothing a molecule wants more than to sit down on the couch and watch TV all the time. And the only time it will not do that is if it absolutely has to do something because somebody is knocking on its door really loudly, like some sort of reactive thing that it has to go deal with. But if at all possible, the molecule is then going to regain its former pose lying on the couch. Like, molecules don't want to do shit. Electrons always want to be as low energy as possible. Charges want to be as stable as possible because that's lazy. Molecules are lazy, like really, really lazy, and they want to be lazy. So electrons don't want to be near other electrons because that makes them higher in energy because then you have this electron-electron repulsion. They don't want that, so that's why the methyl is so much stable. The carbocation, positive charges are unstable. They want to be helped, so having other electrons nearby helps stabilize that, lowers the energy of the molecule. Molecule can relax a little bit more. So does hyperconjugation affect reactivity of the molecule? If yes, does it increase or decrease it? Greater amounts of hyperconjugation stabilize the positive charge more. So if you have a positive charge, the more hyperconjugation you have, the less reactive your molecule is. But, you know, positively charged carbocations don't grow on trees. You have to make them. So it is much easier to make a more stable carbocation than a less stable carbocation. And really, that is what we are going to spend the next 2 or 3 weeks talking about, which is making stable carbocations. We want to make the most stable one we can. Once we make it, it reacts fast. It's reactive. And it's absolutely true that if you can get a CH3 plus, that is stupid reactive. It's so reactive you can't see it, because as soon as it's, if it ever forms, it immediately reacts. I don't think it's ever been observed. I actually think there is no mechanism that has been proposed that has a methyl cation. So, but you know, a primary carbocation reacts almost instantaneously, like functionally instantaneously, like femtoseconds, like immediately. Whereas a tertiary carbocation can actually stand around for a millisecond or a microsecond before it reacts. It'll react quickly, but the difference between femto and micro is a lot. Not to us at all, blink of the eye, all of it, but it's still a lot faster. So more stable carbocations are much easier to form. Less stable carbocations react faster than more stable carbocations, but they're really hard to form, so you don't tend to make them, so you don't tend to see them. So we're going to be talking a lot more about the more stable ones. So I don't know if that helped answer your question, Iacide. Now you just have a final. There's no second midterm. I don't know if that's good news or bad news. My feeling is you have way too many midterms. You know, there's no good way to do this. You either have too many midterms and you're stressed about that, or you have too many marks in the final and you're stressed about that. It all sucks. I'm sorry. I wish we could just do like ungrading and no one got a grade. But then, like, you know, everyone gets confused about that. Like, med schools don't like it. So, you know, it's basically, you know, Hunger Games out here. You guys sicked against each other. So I do want to talk about one example I did get by email. So Alyssa asked a really, somebody asked a really good question. I outed you, Alyssa, but it's a great question, so you're not going to be embarrassed by this. I promise never to announce the name of somebody when they ask an embarrassing question, though please do. It's nice to get those by email because then I go, shit, I screwed up. That's obviously not explained very well in my lectures or my posted lectures or on textbook or on any other resources, because of course you would have gone there first. So the question here is basically, what happens? So, so the question I think some of the confusion here was, aren't these things stable? Why are they reacting? So I think the first thing to look at is like, yeah, that is perfectly fine. Nothing wrong with that. This guy, on the other hand, not so fine. That's a carbon phenyl. We haven't used this abbreviation much. I don't think we've used it at all. Is that. And sorry, that circle thing is benzene. So I can write phenyl minus, that minus, or circle minus, because the circle is faster to draw than 3 lines. That is literally one of the reasons. The other thing is because it kind of shows that, hey, there's resonance. These double bonds aren't really stuck there. They're kind of all rotating around. All this means the same thing. So this isn't stable. That's our problem. So then the question becomes, okay, how does that react? So if I ask this question slightly different, or it's not me, I guess, if the textbook had asked this question slightly differently. All I've done is I've swapped an oxygen for nitrogen. It's an awkward place to draw the lone pairs. I'm going to draw one on the outside. I don't know if this helps at all. If somebody wants to jump in and talk about how the top one or the bottom one reacts, either one. So Alyssa, I like what you're saying there. Let's just think about that for a second. You're not right, but you're close. Your nucleophile is definitely the phenyl. I agree. And it's really tempting to say, look, the oxygen is fucking positive. I did not just say that. I said frickin' positive. The oxygen is positive. The carbon is negative. You stick the positive and negative together, damn it. How many orbitals will we be using on oxygen if we do that? If I just draw that arrow. I know. I've honestly never received a complaint about the swearing. Watch a complaint come up, but I use it. Yes. Yes. Okay, let's just follow through this logic because I want to show this. So you've seen it, Alyssa. Awesome. Congratulations. Let's just follow through this logic and see why this doesn't work. Because if we do that immediate arrow I just drew there, we're in trouble because great, we got rid of the charges, but 5 orbitals. That's not only like an unhappy face, it's more like a like screaming face kind of thing. So we can resolve this. I'm going to put in brackets. If you put something in brackets, it means it doesn't really exist. So you're fine. I'm going to resolve that by moving the lone pair over onto the breaking into a bond. The problem is the oxygen is still positive, and now that one's negative. So I didn't actually solve my reactivity problem. And there's nothing more I can do. I'm kind of screwed at this point. But if, as a couple of people noted, you attack the carbon of the double bond, the oxygen gets its lone pair back. It's happy. The phenyl is happy because it's neutral now. There was a hydrogen here. We didn't draw it, but it was there. Everyone's happy. We have a nice stable molecule. We don't have this shit show where, you know, there's just charges everywhere and everything's unhappy and, you know, orbitals are screaming and professor's screaming and everyone's upset. So looking at the top one, it's exactly the same thing by analogy. Because you have the same problem. Yes, we're going to temporarily generate an N minus. N minuses are not good. I agree. Are they better than C minus though? That was a question. And it wasn't one of them rhetorical ones. It was one of them Socratic ones. Yeah, right. You won. Right, you just won. You went from a carbon minus to a nitrogen minus. That's a win. Then you treat that with water and you'll make that neutral because it'll grab a proton. So when you're looking for the unstable thing, sometimes your reactant is perfectly happy. You're like this guy over here is perfectly happy. It's the reagent that's knocking on the door. This guy's lying on his couch. And the reagent's saying, pay attention to me, otherwise I'm coming through your door and setting fire to your house or something. Actually, phenyl lithium would set fire to your house. So the whole thing kind of holds up there. That's kind of good. So that's this one. There was one other really cool question that came up. That's kind of like, I think we're in bonus time here, so if people need to run, they need to run. Damn it, where was it? View by flag status. Come on, John. No, I did not save it. Sorry, give me a quick second here. I have to go back through however many hundreds of emails I've gotten since this morning. Because I thought that's a good question. I want to bring that up in class because it's a really good question. It came in last night. Okay. Oh, and I had it open. Okay, so the question was, this. Sorry, that's not a question. That is a molecule. Trace. I really hate the subscript trace. I'd prefer if like they wrote trace next to it in full size, but just a small amount of HCl. And it said on a scrap piece of paper, draw the curved arrow mechanism for the following reaction. Once you have determined a major product, draw it in the space below. Remember to include the stereochemistry of the methyl groups. Anyone have an idea of where to start? This is actually one of the questions in the textbook. Hopefully it's one of the end of chapter questions, because I told them to remove all the ones you need to upload stuff in from the textbook, from the in chapter ones, because those are what you get grades for correctness. Oh, maybe if it's draw it, you're okay. You don't need to upload it. You can draw it. Okay, so the question is basically saying, hey, HCl is H+. That's it. That's all it is. Source of H+. That's all you need to think about it. There's a tiny little bit of chlorine in there. Forget it. Tiny little bit. The important thing is H+. Okay. What is the most basic site on the molecule on the left? It's an acid. We're talking about bases because it's an acid. Is it the carbonyl or the alcohol? Double bond O attack H. Exactly. Perfect. Okay, so we do that. Okay. So what we've done here, right, is we can have the resonance structure and we can sort of sketch that in for our edification, where we have the positive charge on the carbon. Anyone can suggest a next step. There's a tiny bit of chlorine in there. We can forget about it. It's not enough to be able to react with everything. So is there anything else that we can do here? I guess the first question is this molecule stable? If it's stable, we're done. Faith with the ring question mark. Yes, we have a nucleophile, right? It's a nucleophilic oxygen. This one's not nucleophilic really because it's not really like this. It's all tied up with resonance, and so it's not really neutral. It's kind of positively charged, and so it doesn't have extra electrons to share, so it's not a nucleophile. This guy has got nothing using its electrons. We count the number of atoms. 1, 2, 3, 4, 5, 6. 6 atoms. 6 atom rings are good. 5 atom rings are good. 7 atom rings are okay. Everything else kind of sucks. 6 is good. Boom. Okay, it's 6. Let's just draw a ring. It's a cyclohexane ring. It's going to be, I'm throwing my pen everywhere, which is really impressive with the stylus. So if we just go back and number all these. So on carbon 6, there is a carbon and an oxygen. On carbon 4, there is a methyl group. On carbon 3, there is a methyl group. Note, I'm not worrying about the stereochemistry right now. Let's worry about the stereochemistry later. That's a problem for later. Let's just get this damn thing sorted. Now, we had trace amount of chlorine, but there's only a trace amount of hydrogen, so let's come in and scoop this up. Make our molecule neutral. There's nothing else in this reaction. There's no water, there's no other alcohol, there's nothing, and we like making rings. So when you can make a ring, make a ring. So we've recovered our trace HCl, which can then go on to react with another equivalent of the styrene material and do this again and again and again and again until everything is converted. Now, to figure out how to draw the stereochemistry on these carbons, it's up to you how you do it. You can assign R and S to these initial carbons. Nothing wrong with that. I'm going to assign, but I didn't ask you to name the molecule, right? I just said draw the product. And by I mean, you know, the powers that be that wrote the textbook. So what I'm going to do is I'm going to assign sort of fake RNSs. I'm not going to try and figure out RNS. I don't care. I just want to kind of know. So, you know, here's H, here's H. If I assign A, B, C, D, where A points towards the original carbonyl, B points away from the original carbonyl, and C is the H. I'm going counterclockwise. Now you can assign R and S. If you find this really confusing, go ahead. It's just, I can't be bothered. It sounds like a lot of work. So where's the original carbonyl? That was over here. This is carbon 4 I'm looking at. So here, so carbon 5 is A, carbon 3 is B, the hydrogen is C, and I want to go counterclockwise. So A to B to C should be counterclockwise. The hydrogen was out. And so A, B, C is counterclockwise, which means that the methyl group has to be back in a way. And you can do the same thing for the other guy. Or you can assign R and S. Or you can build a model kit of this and rotate it. Or you can rotate it on the page. I don't want to do that right now. Basically, that's going to stay the same. The other one's going to flip. The other one's going to be coming out of the plane towards you. Is going to be the answer, because that's what happens. But I think if you can practice rotating that on a page, you should convince yourself of that, that this one here, the answer is going to be the methyl group out. That's cool. And that's a good use of your time. But you can also assign RNS. You can do this kind of fake RNS thing I just did here with this ABCD bullshit. Or you can build a model and cyclize it onto that. So what were the steps we did here? We identified what was reactive. We identified what its most likely reactive partner was. We drew the outcome of that, and we basically did the same thing again. We identified what was reactive, which was going to be the carbon, not the oxygen. We just showed why you don't make a bond to the positively charged oxygen in a double bond. Like that's what we were doing here, is like don't attack the oxygen. You get into this mess, attack the carbon. And again, I think early on in the carbonyl stuff, I said stuff reacts like its second most stable resonance structure. Second most stable resonance structure. The most stable one, of course, has the carbonyl drawn. So I identified that this was reactive. What's its reaction partner? There's nothing in solution, so I'm looking for a nucleophile. I'm looking for a lone pair. The only place I have a lone pair is on this oxygen. It makes a 6-membered ring. That's great. I want 6-membered rings. I get my product. Now, if this wasn't able to make a 6-membered ring, what I would probably do is react it with another equivalent of the same molecule. Another OH on a different molecule would have reacted with that, because there's nothing else present. If I wasn't able to make a 5, 6, or 7, but I was. So I'm okay. So again, next class, this class, like the last 2 lectures, I've been a bit more lecture-y than I want to be. And it's because I think the carbonyl stuff in my recorded lectures isn't as good as it could be. And I don't love the textbooks, so I wanted to make sure I did impart specific stuff. But starting next class, I want to come back to student-driven learning. So if you have questions, I'm going to go over your questions on carbocation stuff. I'll have a few to go through too, but we're going to start talking about carbocations and alkenes and generating carbocations from alkenes. Okay. Thanks, everyone. I'm going to hand over to Samra, who's going to keep going for a little bit longer, but I'm going to stop recording at this point so that, you know, any questions and things don't live on forever.